Here we are again. So we're going to go over database stuff this week. So some people have asked me about these videos and like where do they fit in. I consider them supplementary. So you do want to read all the material in order to prepare for quizzes and tests and that sort of thing. Make sure you hit all the concepts you need to. As far as exams go, when it comes time for an exam, you will have a study guide I'll give you. And but don't necessarily expect that I will hit every single item that you need to know, concept that you need to be familiar with in these lectures. This is just meant to try to put things in context and reinforce certain things that I think are important. Like for instance, in this one, what you guys, I feel like at this stage, what you mainly need to know is mostly this first area, especially when it comes to relational databases, and then a bit about big data and some of the other things. But so I'm going to be focusing on those. I need to pause. Hold on. I forget that I don't even need to tell you. It's not like you're waiting on me. It's instantaneous. That was an appointment reminder. I do have a couple procedures this week. It's nothing serious. It's just kind of investigating some things. So if you bear with me this weekend, if you need anything, I might be kind of not as available as I would normally be. Okay, I should probably just make an announcement about that. So what I was saying is that putting things in context, emphasizing certain concepts, that sort of thing. So with that, I'm just going to use the chapter. I think I used the PowerPoint slides last time, or the slides to kind of guide my thinking on this, making sure that I'm hitting all the stuff the book's covering. Again, not hitting but a guide to like the breadth of the material that's being covered. So I do teach a class on database concepts. I thought about giving like one of the early videos. I haven't decided yet. I might add it as a link if anybody's interested. I probably some of the stuff is relevant, I think, as far as this course goes, because it's the introductory week. So it kind of lays down the background of databases and some things that this doesn't really cover directly. It might go into a little bit too much detail, so I'm going to put this. I think I'll probably put it up. If I do, I'll make an announcement. But it'll be a supplementary video to this video, which is kind of, I don't know, supplementary in a way. But anyway, let's get started. So e-commerce, that already annoys me. The business side of the stuff is like, it's not my favorite part, but I come from a computer science background, so that's where my focus is and my preferences. But of course, they are used. Databases are used. It says e-commerce. They're using all kinds of commerce, right? I mean, most everything now is connected by networks, and you have computers and databases. So whatever. So this is just like introductory stuff and the things that you're going to like learning this. But I just want to get to the meat of this stuff. So database, let's look at the definitions right here. So designed or organized and carefully managed collection of data. So yeah, I would say it's something, a database is just anything that stores data, whether it's paper files and I think I've given the example of file cabinets and stuff before when I've talked about this. And when I've defined data, I think I'm not going to go over that again, the whole given thing and all that. So it's just a fact, right? It's anything that stores facts. Ideally, it's going to be some kind of structured way, so it makes retrieval easier, and processing easier, updating easier, creating new records, creating new data, adding new data easier. There are different ways you can go about doing this, different styles of databases, and that's part of what this other video would cover. It tells you all that. I'll just briefly name them. I won't go into detail about what they are, but there's the hierarchical, and it's different from the hierarchy here. There's a hierarchy of data that this goes over in this chapter, but there's also a hierarchical database. It's a kind of database where your data is organized in a hierarchy. And I apologize if I've gone over this already. These classes that I have this semester are so similar, because I've got two database classes and this class that has a lot of stuff about database, so I forget what I tell each class. Probably should make some notes. But there's a hierarchical database. There's something called a network database. That's where the entities that the records you're storing, the entities are connected like a graph, kind of. You kind of see this also when you get to the relational database, and this is where I want you to focus your attention, is on this model. That's the most common database today. It's the database you're likely in IT to have to interact with since in some way or another for the foreseeable future. Anyway, this might change if there's some kind of revolution, but it's either going to be some kind of big data NoSQL database that you interact with, or like the much more common relational database, which has been the standard for decades. A relational database. This is where I Google again. Let's Google off screen so I get the best thing first. Got a particular thing to show you with this, because when I talk about relations, I don't know if I've talked about relations in this course or not, but it's a very specific mathematical entity. Let me see if I can show here if there's some good examples of relations. Yeah, that's not a great example there. Let me see. You know what, I'll pause. Okay, took a second. I wanted to find something that won't maybe scare you off. I just want to show you that it's mathematical. So this is a random image I found. Took me a second, but it's showing you like a relation has to do with set theory. So this is actually not the best thing, but the whole thing about the terms is nice, because the table is something that relates to a relation in math. So the reason, long and short of this actually is this: I want you guys to know that a relational database is not called a relational database because the tables have relations between each other. Relationships, I should say. Relationships. So this is a characteristic of relational databases, and we'll briefly discuss it later in this video. But a lot of people think erroneously that a relational database is called that because you have relationships between the different tables, which you do. That is a thing, but it's not. That's not why it's called a relational database. It's called a relational database because it's based on the mathematical concept of a relation, which is a thing. What's the word I want? A concept in set theory. So this is showing you how you could like translate between math and databases with these different things. And we'll learn about the database terms. The R table, don't worry, in the N and all that, don't worry about that. But like tables, columns, and rows and that sort of thing are all concepts that we'll talk about in databases. A tuple, it's a good term. Look that up. A tuple is like any combination of things that are taken together, a group of things taken together as one thing. So, and you'll see it kind of called like a 4 tuple, 5 tuple. It depends on how many things are in the tuple. A tuple is something you would see if you do Python. It's an actual kind of it's a structure, it's an object that you use. Usually it's just a bunch of values separated by commas. If you ever do Turing machines, if you learn what those are, you have tuples in that to help you do the logic of a Turing machine. It's too much to get into now, but again, the long and short of that, don't worry about if you know what all these things mean right here. The long and short of it is that, or in a nutshell, I could say that as well, I guess, is that it's a mathematical concept. So that's what a relation is a mathematical term. And what it corresponds to, this is a foreshadowing when I get to it. It's something that in more real world terms and database design terms, you would call first an entity. So basically a noun, a person, place, thing, item, whatever. It's called an entity. And then that entity becomes, when you actually create the relational database, you will have things called tables. Those entities become tables. So relations or entities are tables. And then you can have relationships between the entities and relationships between the relations, I guess you would say it. So anyway, let's get back on track. So database management system, don't confuse these two terms. And I think it's good that they show these two. You will often have this used casually and even by database experts, database administrators, DBAs, to mean database management system. So put it in the database, or is the database down, or whatever. They're talking about the database management system. So a database management system is typically when you're saying DBMS, you're almost talking about some software that's running that manages databases, one or more. So SQL Server, for example, Microsoft SQL Server, that's a DBMS. Access is a DBMS. Oracle, the different varieties of Oracle are DBMSs. MySQL, DBMS. So they're database management systems, and they can manage one or more databases. A database is just it's a collection, a structured collection of, like, the definitions right there, of data, right? Typically, one shade of meaning of that, though, is that it's data that's like all related to some enterprise or business or organization or whatever you want to put it. It's all like all the different tables are put together to run some enterprise in the real world. That would be a database. So a database will have one or more tables in it. And then a database management system, they could have totally unrelated databases. Like if you have on your computer, you can have SQL Server Express running. And you can like have a database for your comics, and then have a database for your small business, and have a database for your coin collection, whatever. Those will be different databases. I hope that gives an idea of what it means for something to be a database. All right, so that covers those two things. And again, read all this stuff. Don't think that I'm covering every single point, but I'm trying to emphasize, both emphasize and also put things in the context, the big picture. All right, some of these, just read whatever. So hierarchy of data, this is talking about, specifically, I'm going to say in computer terms, the smallest piece of data you can have up to like the biggest collection. So this is, I guess they're going to say the fundamental thing here is a character. So you could store at the smallest level, really at the smallest level, you can store bits, which are 0 or 1. There are things that are like true false things, like is this person eligible to do this thing in the database, yes or no? You can use a 0 or 1 for that. I'm trying to remember if SQL Server actually just uses 1 bit, or maybe it's something bigger than a bit, but it's kind of a metaphor, like 0 or 1. I'd have to get into the nitty gritty about how it's actually implemented, but in theory, you could say the smallest bit of data is a bit, a literal bit, which I think is a backwards etymology for binary digit. I don't think it was binary digit first. Maybe it was. I think bit was first, though, because bit just means a very small thing, right? And then they like made up that definition, that etymology for it retroactively, a binary digit. But anyway, smallest thing would be a bit. Whether something exists or not, think in Taoist terms, right? Yang and yin, light and dark, male, female, all those different opposites, binary opposites. And then a field you would take several of these bytes, which is again a character's 8 bits, and that's called a byte sometimes. If you combine those together, you can have something like a word or a numeral, like 1, 2, right? Those symbols are could be stored as characters, or they could be stored as mathematical values. That's two different ways of storing things. So if you know about computers converting between strings, characters, and actual numbers, they are actually two different things. One's the sign, the symbol, like these symbols here, the 098, 054. These are actually characters, right? But they indicate values to us. But in this case, that looks like a social security number, so you don't do math with that. So you would just store it as characters instead of a number. It's not, you're not storing the number. What is this? See where to put the commas. What would it be? 9,840. No, I got this at 98,401,370. That's not what you're storing in the database. You're actually just storing these characters, 0, 9. Of course, you would lose the leading digit anyway, the leading 0, if you did that. So these are things, I know it seems like really persnickety, but these are things you need to, what's the word? Not accommodate. You need to think about when you're storing your data. You need to consider all these aspects about whether you need to store as characters. Does this need to be an integer, a big integer, or does it just need to be 9? Is it 9 characters? I'm not good at counting. I think social security numbers are 9, right? There's 4, 2, 6, 7, 8, 9. Yeah. Or does the phone number need to be 10 digits, or does it need to be a big number, right? Just 10 digits. You don't do math with it. Actually, none of these things. Looks like you do math. So anyway, a field would be kind of, in my mind, that's sort of the smallest unit in a database, because a field usually corresponds to where a record intersects with an attribute. So it's one attribute of the entity. It's the intersection of a row and a column. So I usually consider that a field to be an atomic piece of data. So when you think about the original definition of data, it's just a bare fact, right? What is this piece of data? It's Fisk. Fisco? It looks like a line through there. Is that Fisk? I think it's the last name. So Fisk, what's the information? The information that is that person's last name, because you give structure to the data. There's a column that's labeled last name. So if you find out like the 5th record in this table that we're looking at here with the fields in it, and then so many columns over that symbolizes the last name, you have the one atomic value Fisk there. Atomicity is something that comes up later in the video. In the reading, atomicity comes from Greek atomnein. Atomnein means to cut, and means not being not. So atomic is something that's not cuttable. So you can't break it down into smaller parts. That's why it's called atomic. That's why an atom is called an atom, is because at one point it was considered the smallest piece of matter, right? You can't break it down any further. You get down to atoms and that's it. Of course, we know about subatomic particles now, and in the 40s we did split an atom literally, right? So it's kind of not an accurate name for it anymore, but the original idea is that it's unbreakable into pieces. So that's what your smallest, in my opinion, the smallest unit in a database is that. It's that field, or it's that atomic field. So in this case, it's somebody's last name, Fisk. It has a certain spelling. It is obviously in the mechanics of the database, not logically speaking, but physically speaking, it's made up of several characters. But logically, it's the smallest unit. It's that value, Fisk. What constitutes the smallest value, or the field, can change depending on the structure of the database. So one of the things, I think, this is my other class, so I apologize for that, but for example, you could have a database field for a customer. It's just called name, and it can have, you just put John Smith in there, right? In that particular design of the database, of that table, customers, the name field is atomic. You don't break it down smaller in John's. Obviously, you can in real life, and that's a design decision you would make. You would go back, maybe redo it or do it, but before it gets to that point, it's probably a good idea to break John and Smith down into 2 smaller parts, which will become atomic fields in the final product. So you would have first name and last name, like it has here with Fisk. So John Fisk, right? But think of like a street address, like it's no longer mine, so don't dox these people, but 7211 Terry Drive. That is an atomic address in a way. I mean, it could be in a database. You have a field called address. You'll see this often. It'll just say address, and the value will be the house number and the street, and the road type or whatever. For some database designs, that's the field. So it's atomic in that sense. You don't break it down any further. You could design the database, on the other hand, to have more fields than just that one for the address. So you would have like the house number as a separate field, and then you would have the street as a separate field, and maybe a street type, so drive or road or boulevard or whatever. So again, I'm just trying to the purpose of these videos, I'm really trying to highlight what all these things mean, and the considerations you need to make when you're looking at all these different terms. So a record corresponds to, I think it was tuple in the relational thing. So it's a bunch of attributes you put together to symbolize one entity. So it could be a customer. So it would be the customer's unique ID that you've given them in the database, the customer's first name, last name, the customer's address, the customer's phone number, the customer's email address. Notice I say the customer every time. So you'll have perhaps, and I'm not saying every table in all databases is customer. Obviously, there's all kinds. You have product table, you have department table. These are all different entities, but customer is a common example. All these things relate to the customer, and this is kind of the ideal, sort of the more like plain talk way of understanding what the whole point of a relational model is. A relational model tries to break down things into the most logical arrangement of things that relate to each other. So you got all these attributes that belong to each other, and they're in one table. I'll get to more of that later. And then files, I'm not sure what they mean by files and data. I mean, you can have files inside of a database. I'm going to say, I guess maybe they mean, is it like tables maybe is what that corresponds to. This is meant to show, records, you could have several records in one file and then several files in a database. This is loosely speaking, this is not relational terms. So we'll see how this corresponds to relations when we get to that later. All right, it's been quite a while on that page. Next page. So I've talked about this already a little bit. So an entity is a person, place, or thing, or object, or whatever. It's a noun. Usually it's symbolized by it depends on the diagrams you're putting it in, but it's a singular capital name, not name, but noun. So customer, product, department. It's singular because you're talking about the type of thing that all the things in that are. So often you'll see this violated in everyday databases. You'll have, when you get to the relational databases where you actually implement these things, the table will be called customers or products or whatever. Technically speaking, that's kind of against what a purist would do. I'm kind of a purist on that. I would call my table customer or product, but you'll see in practice, that's the word I wanted earlier. In practice, you'll see pluralized because your brain kind of conceptualizes, if you have a bunch of customer records in a table, it's a bunch of customers, right? But you should think of it more of the type of entity it is. It's a customer entity. It's a product entity. And that will, each instance of that entity, which all the customers in the world or all the people in the world, if you had a people table or if you had a product table, all the products in that company, each individual one will be a record or a row in that table. And then each one of those records will have columns which correspond to attributes. So the product number, the quantity on hand, the name of the product, a description, like a long description, that sort of thing. And that's what attributes are. So roughly speaking, there's a correspondence. I don't know if they have this like a chart anywhere for this, but this is, I would write this down for the future reference, especially if you do databases later. There's a rough correspondence to these things. So we were talking about the mathematical principle of a relation earlier. A relation corresponds to an entity. A relation is the mathematical formalization of what an entity is here. They're the same thing, essentially. And an entity is a table. So if you had like a chart, you would say an entity correspond, like arrow table. That's how they correspond. An attribute corresponds to a column, or really column heading in a way. You'll have a heading at the top of the column and then you have all the values in that column, right? But roughly speaking, you just say it corresponds to a column. And then an instance of an entity, one particular entity in that group of things, so like the customer entity will have a bunch of individual customers, right? One of those customers corresponds to an instance of an entity, and that corresponds to, their terms might be different here, but it corresponds to a record. And a record is a row in a table. So let's see what they've got here. And then we'll talk about keys here in a minute. The specific value of an attribute called a data item. So this is what I was saying earlier. I consider that the atomic. Remember I was going on about atomic in a field? The data item, the individual fact, is the intersection of a row and a column. So you see for this particular record, this symbolizes an employee. This is an employee. It doesn't say what the table's called anywhere. I don't see it. I'm going to say this is an employee table because it has employee number here. The intersection of this column, first name, and this second row here is the individual. It's the first name. It's the data item that corresponds to the first name of this second employee. So Bill. Right, it's a single value that you don't break down. This is the hire date, so this is a date value. Hire date plus which employee it is gives you information. Basically, when you're talking about data versus information, the data here is just a date, right? January 5th, 2001. It's a young employee. Are all these employees young? 95. They're all. Oh, that's hiring, not birthday. I'm thinking birthday. Oh, sorry. It's the hire date. So he's been around. He's been working there for a long time. Stephen Fisk has. Derp. And so anyway, it's the end of. See, okay, that's a great mistake to make though, because what does that tell you? Remember, I just said it's a fact, right? It's just a date. January 5th, 2001. What does it mean? Well, it depends on the context. That's when it becomes information. So like if your information's wrong, or your context is wrong, your structure in your head's wrong, you have the wrong information, even though the data is still the same, right? So it's always January 5th, 2001 in that representation there. And that's one way to interpret it anyway. But it's the hire date of a particular employee. That's where it becomes information. All right. And so attributes also, I should have said this, they correspond to columns and also fields. I would say columns is like the whole category of attributes for that each record, right? Like there's this is the tuples we were talking about before in relations. You got employee number, last name, first name, hire date, department number. That's a 5 tuple. You put those 5 values together, specific values, and that defines a relation. But in table terms, these column headings correspond to attributes. And roughly speaking, people just refer to the attributes as columns. But you can see how each one of these intersections of a row and a column is a field. So those are your terms. Now, what's a key? A key is anything that can uniquely identify a thing. So in database terms, there's all kinds of different keys. I don't want to overload you with all the different terms, but the most popular, most useful kind of key is something called the primary key. A primary key, and they don't really say this in this reading, and I want to try not to make it too complex, but I want you to know about it because it's important later in your database class. Says the key field. A key can be more than one field put together as a tuple, right? We're talking about those tuples again. It's a combination of a bunch of values that define something. In this case, several things I want to say about a primary key. Let me define it first, though. Primary key is a key in a relational database, is a field or combination of fields used in a relational database to uniquely identify a row. In other words, to uniquely identify a record. And also, in other words, uniquely identifies an instance of an entity. So for these employees, the primary key would be an unambiguous way for you to know exactly which employee you're talking about. So one of the good examples they could have had here was Francine Johns, and then another Francine Johns. Kind of a less than usual name, but if you had 2 Francine Johns, which is possible in the world, right? Or 2 Bill Buckleys. Bill Buckley's the William F. Buckley, right? It's a famous commentator from he's passed. Yeah, I always confuse him with Bill Kristol, but William F. Buckley was a famous conservative from like 70s on, 60s and 70s on. Anyway, had a very clipped transatlantic accent that he spoke with, sort of like. Anyway, I'm not an impersonator. Back on track. You could have 2 of them, right? So the way you distinguish between the 2 would be something in a database would be a primary key. Often it is one field, and what they're using here for the key, and they don't say primary key. And the thing is, you can have all kinds of different candidate keys. Anything that uniquely identifies the row can be called a key. And the book talks about secondary key. We'll talk about that briefly, but ideally a primary key will have a few characteristics, and this is off the top of my head. You can double check me on these, but one of them is it must be unique, and it shouldn't change very often. We shouldn't change it. Ideally, it never changes. So, social security number, I think there's something like when you lose one, maybe, or something, it could change. Sometimes people will use an email address as a primary key in a database. That's not necessarily ideal, even though it's unique. You have to have a primary. You have to have a unique email in order to get your email for it to work, right? You can't have two email because the two people with the same email would get each other's mail all the time. So it satisfies that criterion, but ideally it would never change. So that person might have a different email address, and that's kind of not ideal. So that gets into something that's not really addressed about this too. The idea of natural keys, natural primary keys versus surrogate is what they're called. A natural key is a key that you form out of the data that exists in the table. So if this is HR, it's an employee table, you will probably store the social security number somewhere. So, yeah, I was just making sure I'm still recording because I've been talking for a long time and it gets stopped after 45 minutes on my last video. So I don't want that to happen again. All right. Where was I? Yeah. So, social security number is unique and you could use it for a primary key in a database most of the time. Like I said, there might be very rare occasions where it would change. We could still use it for the primary key. But there are problems with that, like privacy, security. Now, if you're HR, you need access to the social security number, so it will be in the database somewhere probably anyway, but it'll be usually protected to where only certain people with certain roles can see it. So it might not be the best way to use as a key for each employee, even though it could be. So you have this idea of something called a surrogate key. And the most common example of a surrogate key is just you start with the first record in the database, and that's 1. Then you add another, that's 2. You add another, that's 3. If you ever delete them, you just typically don't reuse them. You never use, so you might have gaps. Say employee number 3 was fired and you erased all evidence of their existence. Then you would have in your database of employees 1, 2, 4, for example. And it could go up. Obviously, it won't go to infinity because you won't have infinity employees. But that usually accommodates that surrogate key. Obviously, if you just keep incrementing each time you add, you won't have it. Will be unique. Sometimes it's like randomly generated letters and numbers. There's different solutions for this, but so I think some purists like the idea of natural keys, but most people would use surrogate keys now. So something like auto increment, or it's called an identity in SQL Server, is what you would use. One other thing I said, you can do combinations. So as long as you don't have 2 records that have the same value in every field, one example of a primary key, which is hardly ever used, is a combination of all the fields. So, and that's an example of something called a composite primary key. Now, composite primary keys are often used, but not where you just combine everything in the field because it's inefficient and it's hard to predict if you ever have the same data twice unless you have something like a social security number thrown in there, which is unique. So you can see that the social security number is if this is all the data you have, this is all you need for the primary key, but it's still a good idea, in my opinion, to add a surrogate key. Something like 1, 2, 3, 4 auto increment. I hope that's not too much info, but we are talking about keys there, so that's the importance of keys. Secondary keys would be something like email address that, like, your customer's not going to know that he's 1, 2, 3, customer 1, 2, or 3 or whatever, but you might, as an employee, might be able, like a client at the front, at the cashiers or whatever, hey, you're in a rewards plan, put your phone number in. That could be a secondary key because phone numbers, 10-digit phone numbers in the States are unique. They're not probably used in the actual database of the customers of Walgreens or whatever as a primary key, but they can be used to find a particular record or a subset of record and narrow it down anyway. The book used the example of the last name. Hey, what's your name? Smith. You put that in and you get like a smaller set of Smiths. I wouldn't call it a secondary key in that case. That's just a query. You're like, give me all the Smiths, right? So Morrissey and Johnny Marr. But anyway, that's not really a key. A key by definition should be something that could be unique, and a last name isn't. All right, that's my opinion on it anyway. Some of these things get, like, you could debate the meaning of it, but a key should be something that could be unique. there's a concept in database design called candidate key. It's some kind of field or subset of fields that could be a primary key if you want it to be. That doesn't mean it's selected as one though. So going back a slide, if this employee number was not picked as the primary key, it's still a candidate key. In this particular database, if this is all your records, first and last name so far could be candidate keys because each one of these uniquely identifies in this set of data, but you can't predict that for the future, so it would be a bad choice. Okay, where are we at? Okay, so this is more about like everyday use of it. I'm more on the design side, so I want to let you guys read this, just look at the questions and stuff, and I'll let you teach yourself on that part. Data modeling, I got a lot to say about this probably, but some of the stuff that's kind of like glossed over is some of the concept of business rules. So whenever you're creating a database, you want to like this is kind of like on the way towards business rules, what's going on here. So let me give you an example, one example of business rule, and I won't go too much into it, but let's say you have and this is one of my favorite examples because it's easy to imagine, I think, but you have a clinic of doctors, and one of the business rules that you might have at that clinic is that one doctor treats many patients. And then you do the inverse of that. Not the corollary, the reciprocal, right? Would be a single patient. The business rule at this clinic is that a single patient will have one doctor. So one doctor treats many patients, but any particular patient will have one doctor. That's a one-to-many relationship. That's a business rule. So you collect a bunch of relationships like that between your entities. First of all, you identify the entities. So we got doctors, patients, front desk workers, nurses, treatments, medicines, diagnoses. There's all kinds of things you could put in a clinic database. I'm just riffing on it. There's many more that I didn't mention there. Insurance plans, balances for your patients, whatever. All kinds of things you got to identify. And then you describe the relations, the rules of how those things interact. Those are called business rules. And from there, you start to build a model of what your database needs to look like. So, and part of this here, the logical structure, is that model I'm talking about. It's a diagram of how these things interact. The physical organization, these things are tied, but they're not dependent necessarily. You can decouple these things. So you could store, for instance, your logical structure of your database. It would look the same everywhere, but it might be broken, each table could be broken down into several files, or it's hard. The physical thing doesn't have to actually look like the logical model as long as it accommodates the logical model. So the logical model, in my opinion, is more important. The physical organization is like just basically what is it stored on? Are you using Microsoft SQL Server? How does Microsoft SQL Server store the database tables? Are they spread out over several different files? Or are they in one big file? Whatever. That's the physical level. The logical level is the part that's important for database design, though, unless you're the person writing the software for the database management system. It's often good, though, to know the physical level, because when you do backups and stuff, you might need to know which things you need to the physical things that need to be backed up if you're like a DBA. Usually that's built into the logic of the DBMS, but still it's good to know that physical layer. And then these other things are just procedures for dealing with, how long do you keep the data? That thing about deleting, when I said you delete and you go from 1, 2 to 4, if you delete an employee, like those policies, that's kind of meta modeling in a way. And, who has that? Remember the employee, if the employee social security number is stored, who has access, who can see that and who can't. So you have to implement who has access to the database at all. And then if somebody does have access at all, what do they have access to? Do certain people who have access have different access than others? So this person can see this. Sometimes you'll have an employee table that has all the information that the whole company needs to know about the employee, and then the HR, whoever does payments and stuff, will have like a mirror of that or shadow of that same employee table, but they have access to the data that's not available to everybody else. All right. And then they'll have access to tables that other people don't and that sort of thing. The accountants maybe need to have access to the payment processing tables, but the rest of the company doesn't need to have access to those. So that's where security comes in. Authorization, maybe, authentication, all that stuff that you've heard before. Data modeling, this is the fun part, but this is not what I mean when I think of data modeling, though. This is kind of just modeling like the enterprise, how they'll handle it, what kind of level of database system do they need? Do they need networks? Do they need point of sale? That kind of stuff. This is more of like the organizational chart for your data. But this is what I want to get to, the entity relationship diagram. So I'm at 40 minutes. I need to watch it, make sure it doesn't stop. I think I might have turned on a setting that stops at 45 because I have the paid version of Screencast-O-Matic, so it shouldn't be stopping arbitrarily. But anyway, an ER diagram, or entity relationship diagram. Let's look at it. This is it doesn't say it here. It says relationships between data, blah, blah, and this is all true, but it's specifically for relational databases. So I should pause and talk a little bit more. Remember I said it was a mathematical model and stuff. The important thing about that is because of in the set theory is based on that. The reason why it was why it was created, was because it solved some problems with databases. So one of the big things is you have these things called data anomalies. So what a relational model or a relational database strives to do is to make sure your data is inured, is that the word, against these anomalies, these problems. So one of them, and a lot of them come from something called data redundancy, not strictly speaking all of them, but data redundancy is a big thing. So data redundancy is when you have the same piece of data, the same datum, right, that singular field or whatever, that value, for like say a certain record in multiple places in the structure of your database. So an example, if you go back to your spreadsheets, imagine a spreadsheet of patients and you got their patient number and their first, last name, date of birth, sex, all these things that are related to the patient. And then like the last field would be doctor. And then you have like Dr. Smith, Dr. Jones, Dr. Kildare, or whatever. And then you have the doctor's phone number after that. That's data redundancy because the doctor's name at that for the clinic and his phone number should only be in one place, stored in one place. If it's in a patient file, and let's say you delete all the patients just by chance, like these patients leave and you delete their information, and it just happens to all the ones that Dr. Smith left, you would lose the phone number. That's called a deletion anomaly. What if you change the phone number? You have to change it every place it occurs. Relational models, because of the way they work, through a process called normalization and decomposition, strive to make it to where any piece of data is stored in only one place. And this automatically, this structure will lend itself to automatically encouraging your data to be accurate and up-to-date and consistent. Because if you only store it in one place and you make sure that that one place is correct, then, it's not 100%. Somebody can still type the number in wrong or whatever, and that means it's wrong everywhere because it's wrong only where, right? It's wrong in one place, so it's wrong. But that's better in a way than having the right one half in half of the fields where you store it and the wrong one in the other half, right and wrong. So, the drawback to that, and I want you to remember this, if you just hear me rambling this whole time, like focus on one thing. The thing about a relational model is that there's always a strife between keeping all your data anomalies ironed out by using the relational model. So breaking things down to where everything's consistent and stored in one place in a proper structure versus performance. So one of the drawbacks of relational databases, like for instance network databases, I think have a higher performance because you just have a bunch of references to different things, and you kind of look them up. Relational databases, you break down the tables into smaller tables, and then you have to like sometimes recreate the you have to put things back together to get the information you want. So one quick example, this is better with like a figure or something to show you, but one solution that would be more relational, if you go back to that patient table I talked about, it has the doctor's name and his phone number for each patient that has that doctor. One way to solve this is you would just have a primary key for the doctor, say doctor number 1, and then you just put you have a doctor column in your patients table. This is called a foreign key. You just put 1 every place where it's Dr. Smith. Instead, you put number 1, and then you use that 1 as a reference to the doctor table where that doctor's stored in one row, one record, Dr. Smith, Dr. John Smith, and his phone number's in that one place. So you have to do this cross-reference where you put things together from 2 tables to get all the information. What is this patient's phone number? What is the phone number of all let me put this way. What are the phone numbers of all the patients in the database? You would have to find that reference, that foreign key, doctor number 1, doctor number 3, doctor number 4, and that would connect you to another table where that phone number is for each of them. So you have to like recombine things that are broken down, and that's where the performance drag comes in. That's not to say that there are ways to make that better, like make it faster. The thing's called indices, clustering, all kinds of techniques, but you don't have to know that now. But I just want you to know the pros and cons. So here's an ER diagram. It's not a great ER diagram because there's more to an ER diagram than this. This is a very simple, this is a very simplified version of what's known as a crow's foot model. There are a couple different dialects of ER diagrams, entity relationship diagrams. Varieties, that's the word. Crow's foot is one. The original ER diagram, something called the Chen model. The original paper you can find is from like the 70s or before. Chen diagram, original paper. He's the guy. Chen is this guy who came up with the original entity relationship model for modeling these relational databases. And you can find the PDF. Of course, I can't find it right now as I'm Googling in this other screen. If I add the word paper, maybe it'll come up. I recommend, if you have time, maybe checking it out. Here's what the paper looks like. It was in the ACM journal. I might have mentioned this briefly. I can't remember which classes I mentioned this in already, but the copyright here is somewhere. But it's an Association for Computing Machinery, March 1976. This is not the whole paper, because there's more to it than this, just the first few pages. But his diagram looks a little different. Here's the relational algebra stuff that I was talking about before. This is not showing the actual. It's frustrating, actually, because Chen ERD. I'll find a quick example of one. This is kind of a stylized one, but it'll work. So you have entities which are in rectangles, singular nouns. Remember I said tables should be singular nouns? So you have a book table, a chapter table. Then you have relationships signified by diamonds. And this is a weak relationship. This is saying that you don't have a chapter unless you have a book. That's what makes it weak. That's why it has double lines. You got a verb in there, so a book contains a chapter. This is how relationships are done. Again, remember, a relation is an entity. So inside of this, you have you put all these attributes together, which are the ovals, and that put these all together, and that defines an entity called a book. So a book is a title and a book ID, as far as this model goes. And a book and a title ID has a relationship of containing a chapter, which has a title and a chapter ID. And this indicates primary keys. This is a weak entity. So this is a chapter does not exist without a book. So that's why it's got double lines. So this is called a weak entity, kind of like a dependent of an employee. If you had it in an ER diagram for your company, and a dependent does not exist unless an employee exists. So that's a weak relationship. This is what a Venn diagram looks like. This is one to many, right? One book has many chapters. A chapter exists in one book. The one in the N indicates the one to many here. And also, this is a mandatory participation. These two lines, this is saying that a chapter must have a book that it exists in, but a book may not have chapters. Or is it the other way around? Yeah, I'm not sure about the participation here, but an example would be, say, like a patient and doctor. You're not a patient unless you have a doctor, right? But a doctor might be hired by the company and not have any patients, has 0 or more patients because he just hasn't been assigned any yet. It depends on how you define it. It depends on your business rules. Here's a more classic looking ER diagram for Venn model. But see, notice it has diamonds, though. This arrow, I think that's usually part of it. Okay, that's a Venn diagram. And then the crow's foot, it's a variation of that, where some of these things are just drawn in a different way. So and what you'll notice in real life, if you ever see these diagrams, is that there are a lot of versions that are kind of mixed, because I think this is not, strictly speaking, maybe or maybe not a crow's foot diagram because of the line here. Maybe it is, but this is an entity just like in the other one. And this is showing you the relationship. So this is the optional participation I was talking about. So a doctor might not, he has 0 or more patients. This means he has at least 1 patient and maybe more. This means that it's a single thing and only one thing. So this would be the other side. This is doctor. A patient has, and usually you have these on both ends, right? So one doctor has many patients. A patient has one doctor. Let's see if there's examples here. So yeah, one student has 1 seat, and a seat has 1 student in it. A lecturer has 0 or more courses. Maybe he doesn't have any courses that semester, right? He's researching or on sabbatical. But a course has only 1 lecturer, which in real life, and it depends on your business rules again. Like even in the sense, like at Pellissippi, I think I'm going to say there might be occasions of team teachers on paper, but even if you have 2 lecturers come in, the class kind of belongs to 1 instructor, professor, right? So that depends on how your business rules are defined. So at Pellissippi, I'm going to say that a course has 1 and only 1 lecturer or instructor. A student can take 0 or more courses, and a course will have 0 or more students in it. So the course exists, but maybe doesn't have any students assigned to it or whatever. What you're going to see is there's something that happens between these two later on, but we'll talk about that later. So that's the 2, Venn and crow's foot, and often people mix them up. So you can see how this is a simplified crow's foot because you just don't have the participation lines or circles. Anyway, salesperson serves more than 1 customer. A customer places 1 or more orders, or 0 or more. Again, the 0 or 1's not here. An order will be on an invoice. You'll have an invoice for an order. The order, and it says line items here. You can have a product can be on many orders, right? And an order can have many products on it. I ordered like X, Y, and Z. 1 customer orders X, Y, and Z. That's many products on that 1 order. X is on this order, and that order, and that order, and this order over here. So a product can be on many orders. So that's a many-to-many relationship. And remember I said there'd be something in between. You can't implement those directly into a database management system that's relational. All the ones I know anyway. You can do it in a network model, I think, but in an entity, in a relational database management system, in a relational database, you can't have many-to-many directly implemented. So what you have between them is something called a bridge table, a junction table, an associative entity. And what it does is it turns a many-to-many relationship into a two one-to-many relationships. So if you imagine line items, you would say on this order I have this product, on that same order I have this other product, on the same order I have another product, and then on a different order I have a different product, and so on. So remember I said that a primary key can be a composite. That's how it works when you model it in a database. You'll have a table and it'll have at least 2 fields, and each field will be a key. It's called a foreign key. You take the primary key of this product, primary key of the order, and combine them together to make one big primary key. So order number 1 has product number 1. Order number 1 also has product number 2. So each line would symbolize which product is on which order. I think that's a little bit too much detail at this point. I'm going to end up teaching a database class. If I keep going into that, I didn't mean to exit the reading. Actually, let's go back to part 1 and database systems and big data. Go back to the reading. The modeling is my favorite part, though. That's kind of why I wanted to harp on the entity relationship model. But this is the typical way. What you'll do is you assemble all your business rules. You make all, like how many patients does a doctor have? Can he have 1 more or whatever? How many chapters does a book have? You model all this stuff. You write out all the rules, define the relationships between them, and then you draw a right-brained representation of it. And what you'll see is that, this is enough to make a small database right here. It's not really, practically speaking, what you would see in real life. It'd be more complex than this for most solutions, but you could make a small little database for a small, company. This model would almost help you do. What's missing are the columns, or the fields are missing, and they usually occur as bubbles around here in the drawing, and they become columns in the database table. So this will be there'll be a salesperson table, a customer table, orders table, an invoice table, a line item table, a product table, and then each one of these tables will have columns, right? So salesperson ID, salesperson first name, salesperson last name, salesperson salary, maybe salesperson hire date, etc., etc. Those are usually drawn with bubbles in these ER diagrams, but they'll become column headings in the table. All right, next thing. So this is showing you the table stage. So once you've drawn out the relationships between everything with your business rules and all that, and determine what should be modeled, then you can start designing what the tables would look like. So this has got the data already in it. You wouldn't necessarily have that yet, but you would definitely have this be the project table, and a project has a project ID is essentially what it is. It just says project, but loosely speaking, you say, which project is it? But we're saying that it has an ID, so it's a 3-digit number, it looks like. And then a description of what the project is, and then what department that project is part of. And this is where the foreign key comes in. So what you'll see is that a project is in a certain department. Which department is payroll? Payroll is 257. What's 257? It's this unique field. Just want to say, usually the primary key is listed as the first column. It's not necessarily a rule, but it's a convention. We're saying that each one of these numbers here, and here uniquely identifies these records. So this is the payroll record. This is the widgets record. This is the sales manual record. And the payroll record is in department accounting record. All right, widgets are in manufacturing probably, yeah. And sales are in, now this just happened to be in order, but that's not a rule or anything. It just, somebody was lazy in the design of this in their example. But 598 is marketing. So, and then the manager table, a manager is the manager of a certain department. So what department is Francine John's manager of? She's a manager of accounting. Bill Buckley's the manager of manufacturing. So this is how, this is a simple example of tables, but they don't get that much more complicated. This is what a relational database management systems tables look like. So if you're thinking Access, Oracle, MySQL, SQL Server, these are examples of what you would actually have. Usually you'd have more fields and more records, you'd have more columns, but you could have them, in theory, this small too. All the values that an attribute can be, that's a domain. For example, date of birth can be dates, probably within a certain range, right? a quantity of a product on hand would be an integer from 0 to whatever, maybe some limit. You could maybe allow negatives if you want to show loss, right? But so these are things that's metadata about all these things. All right, we're about an hour in, so I want to kind of speed this up a little bit. But projecting, this is how you decide which columns you want to look at in a query. Joining, I mean, this is what I was talking about before. In a relational database, you have to do joins a lot, and joins means using those foreign keys usually is how you do it, relating two tables together through the foreign keys to get pieces of data from more than one table and putting them back together. So you see how, let's just put it this way, if we could have combined these into two tables and it wouldn't be a very nicely what we call normalized table. So you could say accounting has, you see how it's manager SSN. We could, instead of putting that there, we could have just put John Francine like out through here, right? What am I trying to get at with this? Joining. Okay, so you might ask this question: who is the manager for accounting? Well, it's this social security number. That doesn't help out a human being, right? I don't have your social security number memorized. But because of a join, there's something called a join. What you do is you cross-reference this foreign key with this primary key, which is what I just did in my demonstration. And you can find out that the manager for accounting is Francine Johns, right? They relate this way. That's how a join is done, essentially. Selecting, eliminating rows. You can say, hey, who are the employees who've been working with us for more than 20 years? And that would only put that one guy up there. That was 2001, if you remember that. All right. It's too much detail. This is an ER diagram, by the way, of those tables we just did, it looks like. Remember, because they were projects, departments. And so this is how this step usually comes first, though. All right, and this is showing what I just told you about linking things back together. So you want to know you have to, sometimes each piece of data you need, like what are all the projects that Bill Buckley is responsible for? Well, you have to do some cross-referencing to find out, I don't know, is it sales or widgets? Sales, I think, sales manual, whatever. See how it's spread out over many tables. This is what cuts back on the performance. But the benefit is you have all this stuff stored in one place, and you don't have you can't really see redundant data in this because they didn't give you an example of redundant data. But yeah, so it's again, it's integrity of your data, accuracy, correctness of your data versus performance, just roughly speaking. All right. Oh, by the way, this is an example. This slide. This looks like Access. If you want to know what Access looks like, if you haven't looked at it yet. Access is not most people's favorite database, but it's fine for like a small office or something. It's very user friendly. Depending on what you mean, it's more user friendly than like SQL Server or something, but it's not as robust. So you don't really want to. Part of what you're reading in this is like what's appropriate for each enterprise. So if it's a small office, Access might work. If you've got a bigger enterprise, you might want Microsoft SQL Server. And there are several levels of that start off like for a few thousand up to hundreds of thousands of dollars. So that's going to depend on, this is what this is talking about right here. So you have to use some analysis to see what solution is right for you. The cleansing, I'll let you guys look at that. That's not something that we're going to talk about. I don't know why it's talking about relational database management systems now, since I already went over it, but I guess I've already talked about a lot of this. I'll let you read it, but ACID, you want to know this in general for other things. There's lots of things that go by the ACID principle. So that's atomicity, consistency, isolation, durability. So atomicity means that in the terms of like, often you use this in terms of transactions, which I think is their example here. So if you have two competing transactions, let's say you have 10 products and you need to sell 10 to one well, let's say you need to sell 7 to one person and 6 to the other. ACID is one way that you make sure that your data is correct by resolving those transactions and making sure they don't interfere with each other. So like if you started, like maybe the guy that needs 7 starts deleting from a table of products, you know, there are 10 products, and he gets like 3 of them, and then the next person, the other transaction, will go in at the same time and starts taking some more of the products, and you'll end up with like your data will be off, right? So atomicity means that a transaction, once it starts, completes or it rolls back. So you don't break it down into pieces. You don't do part of a transaction. You do a whole transaction or not. And atomicity can be applied to other things too besides transactions, but the whole idea is that it's all or nothing. Atomicity, not broken down. Again, Tomnane means to cut, like with a sword, and ah means not, so don't break it down. Consistency, you do it the same way every time. Isolation, you keep things, data and stuff that are separate from each other that don't need to be wrapped up together. And durability is the idea that it sticks around until you need it's persistent. It's saved. You make sure it's saved before you go on to the next step, roughly speaking. So I'll let you read in that more. They probably do a better job of describing it than I did, but it's just a principle that you go through to make sure your stuff works correctly, especially when you're handling data. All right, any other? So SQL, this is what we need. I'm glad they talked about this. They showed, I think I've said this in other classes, it's pronounced SQL because it was originally called SQL, a structured English query language, but there was something else called SQL, which they don't mention that here. There was a trademark issue, so they went back and just called it SQL. And I think I've said this in a video before, but both SQL and SQL are acceptable. I want to say I've seen SQL as being the preferred by somebody in industry authority somewhere, but I still like SQL because it was originally SQL. They just couldn't, because of trademark reasons, keep calling it that. And you'll hear a lot of people say SQL. I feel like it's the purer way of doing it, saying it. I did a whole thing about backronyms and acronyms versus initializations and the difference between the two. An acronym is an initialization that you can pronounce. So you can sort of pronounce SQL. You can't pronounce IBM, right? It's IBM. That's an initialization. This is an initialization that is an acronym because you can pronounce it as SQL, like it's a word anyway. Here's another acronym, right? ACID. You don't say ACID. So this is an initialization that you can pronounce, so it's an acronym, which means high name. Like acro means high, like a mountain, and NIM's name, I think. I think I'm right on that. So it's like a higher level of name or a meta name. Anyway, SQL, what is SQL? SQL is what's known as a fourth generation language. I might have briefly talked about this earlier. It's a language where you describe the task you want to do, and then underlying logic takes care of it for you. Third generation languages are most of the programming languages you know, like C, C++, Fortran, Pascal, Python. These are third generation languages. Below them you have assembly and machine language, which is more like the actual binary language of the machines that like the computers. So there's levels of abstraction that are easier for a human to understand. SQL is considered fourth generation because you're kind of saying, hey, I want these columns from this table, and leave out all the columns that have all the records that have values in this column that don't match this thing or whatever. That's sort of the style of how SQL works. Underneath that, there are for loops and stuff executing. So that's one level down. So it's considered a fourth generation language. Sometimes people categorize stuff like Java as fourth generation language. I don't, though. But if you want supplementary info on that, just Google this. This is the abbreviation for talking about these different language levels. So 1GL, 2GL. For first generation language, second generation language, etc. And they'll maybe go into more detail about what they are, but Yeah, see, this is doing Python. I wouldn't do that. I would actually put all these down here, and SQL is the only one in this list I would. But you know, it's debate. It's something you can debate. And that 5GL, fifth generation language, is even more of a debate. So we won't even talk about it. But it's a way. So let's finally define what SQL is. SQL is the language that you can use to speak to relational databases. So that's the key thing. Relational databases is designed to perform operations and get information out of relational databases. It's a way of talking. A human being can can learn it to talk to a database to get the things done that he needs to do. A lot of the things that will, like a form that you pull up to enter a new customer into a database, SQL underlies that. There's a front end that the user can see and it's user friendly, but underneath SQL is operating to make those things happen. So when you insert a new customer, you fill out all their attributes, their name and address, phone number, all that, and then you have insert into customer, and then you have the values, and then you kind of list off the values. You can also put it with the column names, but I'm not going to get into specifics of the syntax of SQL. There's variations there, but the point is you learn that SQL syntax, and that's kind of the back end level that the DBAs and the database managers and stuff will need to know to communicate directly with the tables in the database. The key thing is it's relational databases. SQL was invented for that kind of database. So here's an example. This is saying, let me translate this in English if I can. Give me the client name and the debt of all the clients in the client table where those people have more than $1,000 of debt. That's what that's kind of probably saying. So it will show you just those records of the people with more than 1,000 in the debt column, and it'll show their name. Give me the name and the number, probably a unique ID, maybe the primary key. Give me the name and the client number, not necessarily though, and the order number from two different tables. So, and only the tables where the client number of the client table is the same as the client number that's in the order table. So there will be records for each order, like say a customer ordered several different things in an order table. All the records in that table, all the rows where it's the client number as a foreign key is equal to the client number in the original table. You're getting stuff from two different tables. This is the join we were talking about earlier. So you're getting the client name and the client number from the client table, and you're getting the order number for that client from the order table, but only the records you want to see are the ones where these two things are the same. That's how you match them up correctly. Otherwise, you get a combination of all the different rows. It's called a cross join or Cartesian join. And there's a way to expand this, I know. This is UI stupidity on my part. 112, not too bad. Here's a more esoteric DBA thing where you're giving the DBA user named Guthrie the permission to perform insertions onto the client, so you can add new clients. This guy in the database has permission with this account to add new client records to the client database. There's a lot more to SQL than that, obviously. That's just a small sample. But again, the purpose of SQL is to do operations on relational databases like that. Add a new customer, update the debt when they pay some of it or they add more to it, update that value. Drop the whole table because we stopped using that table when we redesigned it, which is probably bad. But anyway, delete a whole record from a table. We already talked about inserting a new record. You can create things called views, which are stored queries that you can just pull up by that name in the future. Triggers, procedures, all kinds of stuff. We won't get into too much detail for you at this level. When you have your database class, bring up this video before you go to the first class, because I've covered a lot of stuff you'll learn. And then there's the whole the division of like how you categorize the language for databases, the data dictionary, data definition language. This is also some of those things I just taught, like create a new table or drop a table. That's usually considered part of data definition language. So it's DDL all has to do with how you describe not the data itself, but the structure that holds that data. So creating a new table would be DDL. Saying that it can only be numbers is DDL. Saying that you can only have 50 characters, that's DDL. And other things like that. Metadata is the short answers related to metadata anyway. The data dictionary is that too. All the possible values something can have. The type of data, I already said that, like it's a number versus a bunch of letters. That's data dictionary stuff. I think we're getting close to the end of what I want to cover. This is showing the difference between like the logical arrangement versus how it's actually physically filled on the. We talked physically stored, filed on the disk. Anyway, I talked about that a little earlier. Okay, so this is showing you. This is basically what this slide is about. Is like, hey, Access makes things easy for you. So you see how this kind of looks like an ER diagram, one to many. You can create a query in a visual way instead of writing the SQL. Now, if you look at Access, you can see the translation of this query into the SQL. There's a way to pull it up. So what is this one actually doing? It's saying, give me the price total in descending order on that column, the order date, the customer ID. Now you can see the final result here. So it's giving me a price total for a certain customer on a certain order, I guess, what that is. You'd have to know more about the actual structure of the table to know exactly what question's being answered here, but it looks like that's what it is. Like, hey, what's the total of maybe all the products on that order? Looks like maybe. You can see there's more than one order from one person. So this person had 2 orders on the same day for the same amount. That looks like a bad query actually, but whatever. We've already seen examples of that, but data manipulation language this is sometimes called DQL, data query language, because you're just getting information from the table, you're not changing any of it. If you update a value or delete a row or add a customer, for example, add a record, that's DML. There's lots of tasks for DBAs. Database administrator is a role, a job that you can have where you're the person in charge of. It depends. Like if the database already exists, maybe you just need to maintain the current structure. But if you ever need to change the structure, the ERD, the entity relationship diagram, the model of it, like the implementation, DBA would be the person who does that. The DBA comes up with the backup plans. DBA comes up with the security, like keeping SQL injection and stuff like that from happening, or probably in cooperation with people working on the front end and stuff, the programmers. DBA will design the tables. If he's the first person to do it, it'll be like, this is going to have this primary key, and I'm going to normalize it and all that kind of stuff. He does all. He's in charge of all the structure of how a database works, and he's also in charge of how it's implemented, like which database management system you're using, what indices to put on things to make searches faster, stuff like that. That's the DBA. And it could be, the thing is, you'll find out if you go into the real world, that role, there might not be a DBA. Like a bunch of programmers together might collectively be the DBA, or there might be one of the guys on the team who does the database stuff, but other people have some of those powers too. It's all mixed up sometimes. If you're lucky, you'll have a DBA or two who actually take care of all the essential stuff and have a great policy and implementation of their database management system and all the databases on it. I'm going to say if you're less lucky, it depends on your perspective. Sometimes it's nice to have more control over the database if you're a programmer, if you know how to do databases. A lot of programmers don't. It's the thing. They might know how to do queries and stuff, but they don't know underlying, like how the table's really constructed. And sometimes you see, like you'll go somewhere and you'll see how the tables are implemented. And if you know anything about how to properly model and design a database and normalize and all that, sometimes it's a disaster in practice, but people seem to get by. So, but database management, database administrator, DBA is the person in charge of like the database in short. Where are we at? 1:15. So this is by the way, this CouchDB is not relational. I don't know why they have that. But one of the things you'll notice about there's something called NoSQL, and there are other database types out there besides relational, especially these days, and they're usually for the purpose of like either unimportant stuff that's ad hoc, small little projects like web things, or very huge amounts of data that a relational database could not manage in an effectively quick way. Just roughly speaking, that's the difference between the two. CouchDB is NoSQL. So NoSQL originally meant not SQL, not relational. These days they kind of changed the name. If you look, not only SQL instead of NoSQL. And the reason why it's called that is because often they won't be relational underneath in their mathematical model that we went over, the whole relation, attributes, normalization that we briefly talked about. They won't be that structure. There's all kinds of different varieties of NoSQL. There's one where you just have key value pairs, like a dictionary kind of. It's just a big list of them. And you might have redundancies in that, and you're not worried about the redundancies. And there's other like graph versions where you have graph nodes of related things, and Facebook has like a document system or something, but I don't know the details of how they work. But they're not SQL is the point. They're not relational is the point. Some of these database management systems, though, or database schemes that are NoSQL, do allow you to use SQL or SQL-like queries, that structure of language, to interact with them. So that's why it's called not only SQL, even though they're not relational. And even though SQL was designed to work with relational databases, some databases that are essentially at their core not relational still allow, because SQL is so popular, and it's a straightforward way of talking to databases, that they accommodate that language. So that's why it says not only SQL. And CouchDB I don't think it should be in this list. I'm pretty sure it's NoSQL, but I don't know. I want to say it's key value pairs, but I don't remember exactly how it's implemented. There's some stuff about, business stuff and cloud, more like cloud and service stuff that you can look up here. I want to allow you to do that on your own. So self-teach yourself that, because we're getting into the area where big data. I think there's going to be a little project you do where you research this later in the semester. Don't worry about it now. So I'll leave that. Just read this stuff on your own for now, and we'll approach it again later in the semester. I think you're overloaded at this point, especially on the relational details I gave you. So just like make sure you see the main topics here. But big data, just like in a wide view of it, it's like the kind of data that's generated by, let's say, Facebook posts, Twitter tweets, right? There's billions of tweets at this point a second, or thousands a second, millions a day. Billions a day. I don't know how many. It's a huge amount of data. You'll still need to be able to structure it. Like when you load your account, it needs to find your tweets, right? It needs to find how you can address other people's tweets. I'm just thinking off the top of my head, Twitter. I'm not even on Twitter. It's not my thing. But look at all the data that Facebook has to manage. It's huge amounts of data, and it's bigger, bulkier data than, say, tweets. What else? Like maybe the data is generated by some kind of device with sensors, like every several times, like thousands of little updates per second. The kind of data that financial markets, GME, GameStonk to the moon with diamond hands, right? Apes, apes together, whatever. Yeah, I've been watching that stuff. That kind of data, it's huge amounts of data. I want to say that has to be accurate though. So I'm wondering what level. I'm not even sure how you manage like stock ticks, but that has to be accurate. So you do have to have some consistency there, but you also have to have high performance, and it's lots of data at once. A lot of the stuff that goes into machine learning. So if you take all the data from all the stock prices in a certain and different what do you call them? Technical indicators to try to predict the ups and downs in the stock market using something called quant. quantitative analysis of financial data. Big data is involved in there. This is where you go over into like data analysis and data warehouses and that sort of thing. Like, how do you store the data? How do you process that much data? That's where the whole big data warehouses things come in, and data analysis for like business and analyzing a business's data to try to predict trends or whatever. Like, hey, what are customers interested in? What are they clicking on? That kind of. This is all big data stuff. So I'll let you review that here, and I think we're kind of done. You can also like go into a little bit more detail on NoSQL that I was going over, but keep in mind it's NoSQL is by definition not meant to conform to a relational model. It's a more loosey-goosey. Here's some key value, graph, document. I'll just let you guys review that. Hadoop, this is what I think we'll have it's a big data framework. We'll talk more about this later. And memory doesn't. All the databases in the RAM, so it's quicker. That's briefly. I've never heard of it. Honestly, I've never heard of the distinction of this. This must be. I don't know how new it is, but it's something I haven't really encountered in my life. I see that there's like some E-Trade, right? Stonk stuff. So anyway, I'll let you guys go over the rest of it. Like I said, I might put up I always look at these too. These key terms are helpful to organize what you've just like read or listened to in the discussion or whatever. Make sure you know what these terms mean. Quiz yourself. I should probably add that instead of case studies, honestly. So I'm debating whether I'll add whether it's just confusing or overwhelming, but I might add the other video that I have in the other course. I might actually use this video in their course. So both sides will hear me talking about that in this video. But hope that was, again, take these videos in chunks. Don't like sit down and watch this for an hour and 20 minutes. There's a line through. Is that a 6 or a 0? Basically an hour and a half. Don't try to consume it in one sitting. Manage your time and do chunks. Take some handwritten notes. Check the reading and say, hey, do you talk about it in the video? Maybe put it in the background and listen to see if I talked about it if you're unclear on it. But also always just ask me questions or arrange office hours. I was in the middle of grading. I'm in grading another class. I just finished your grading. So, again, let me know if you have any questions about the grading. But I wanted to take this moment to make sure that I get this done and out because it's Tuesday already, and I want you to be able to have time to watch it. Okay. See you in the next one.